So assalamu alaikum warahmatullahi wabarakatuh. So here you see the proof of Ehrenfest theorem that I am going to explain it right now. Okay. For this to prove Ehrenfest theorem, the first thing you require is the first ingredient is the time dependent Schrodinger equation. So as it is known to you that the time dependent Schrodinger equation is given by I h cut dt of dou t of psi, that is the partial derivative, minus h cut square by 2sm dou square by dou x square of psi plus v of x psi. Please remember that this potential is a real function. Now if you take this complex conjugate, what becomes is minus I h cut dt dou t of psi star minus h cut square by 2sm dou square dou x square psi star plus v of x psi star. Now what we do is this. We consider we consider the time variation of the expectation value of the position operator, and we know that the expectation value of the position operator is given by integration over the entire real space from minus infinity to plus infinity psi star x psi dx. Okay, by the way, I am solving for 1D. So this is then you do the differentiation and you get this result. Okay, and then what happens is this, and then you take you put the value of d psi star by dt and d psi by dt from here. From d psi by dt result you put it here from here, and d psi star by dt result you put it from here, and you get this particular value. I think that is very easy for you to understand. And then what you do is this. Check out v psi star x psi dx. Since v is a real function, so this v psi star x psi dx and v psi star x v psi dx, these are going to get cancelled out. So what remains is this only, I h cut and 2sm. See, you need to do some kind of simplification. H cut square by h is h cut, so here, and minus is plus. So I have first taken this term I h cut 2sm psi star x d square psi dx square d square psi dx square minus, here see, minus d square psi star dx square x psi dx. Okay, and then what you do is this. The little bit of simplification we have done. I h cut by 2sm, and this x psi star is as it is, x taken inside. But here there is a trick. That thing is that this is a kind of modification that is being done along with some kind of compensation here, along with the minus sign. So if you expand this, okay, you will get this, and there will be a term like this which will cancel out. So that means if you break down this one, you are going to get this term along with an extra term which is this. So here that is why I have subtracted that term, so that gets cancelled out. So it is as it is. Okay, it is as it is. Now what you do is look at this term very carefully. We are going to do some kind of simplification, very easy simplification here. Just check it out. Psi star d square dx square x psi minus this particular term can be written as ddx of the first order partial derivative of the entire thing. So what happens if you take it inside psi star, what you get, d square dx square x psi minus d square dx square psi star x psi. That means you get the original one. So I have given equation number 3, that was equation number 2, and 1 was somewhere here. Yes. So if you use 3 in 2, what you get is this. The time variation of the expectation value of the position operator is I h cut by 2sm. Please remember this is equation number 2. So that what you get is in place of this one, I am writing this one. So this is getting replaced by this. So this entire term gets replaced plus what, and there is a kind of modification. Check carefully. I need to introduce the momentum operator. So we know momentum operator is minus I h cut by 2sm. So look here, minus I h cut is taken inside here. So minus I h cut is taken inside here. It becomes this. Okay, minus h, and then so it remains 1 by plus 1 by m is here, plus 1 by m is here, and integration minus plus infinity as it is, psi star as it is, but only the thing minus I h cut is taken inside ddx of x psi dx. So that is equation number 4 for you. Now check carefully this particular term. That term that we got before, minus infinity plus infinity ddx of the entire thing, can be you have to integrate and get the result. So if you see, check it out, here dx and here this dx, there's by some kind of operation we get this result, and it is running from minus infinity to plus infinity. So we know that a wave function vanishes as x tends to plus minus infinity. Vanishes means 0. So this entire term that you see, the result of this particular term is this, that is when x is minus infinity to n plus infinity, the entire term becomes 0. So the previous equation number becomes, okay, just 1 minute, sorry, that has to be equation number 5. Hence the value of equation 5 becomes 0. Using this result in the previous equation, we have ddx of the expectation value of x is 0 plus 1 by m of minus infinity to plus infinity psi star. This is the momentum operator, famous momentum operator, and psi dx. But you know this one, right? Momentum operator is minus I square ddx. So if you write down ddt of the expectation value of the position is 1 by m, this one, that is nothing but 1 by m of this entire thing that you see can be written as the expectation value of the momentum operator. So m ddt of the expectation value of the position is nothing but the momentum operator expectation. So that is equation number 6. So the above result is was mass into average velocity is equal to average momentum. Now again, if you differentiate this with respect to time, what do you get? M again differentiate this with respect to, you get what? D square by dt square of this expectation value of the position is equal to, if you just differentiate what is dp by dt, that is nothing but force. Again, we know force is the scalar gradient of the potential minus dv by dx. So that is what you get, psi dx. So that is nothing but expectation value of f. So that is equation number 7. F stands for force here, right? So that is the Ehrenfest theorem, which says that mass into average acceleration is equal to average force. So that was a brief explanation of the Ehrenfest theorem. So I hope you understood. So assalamu alaikum wa rahmatullahi.